God, how do I turn off the notifications? This keeps popping up. The other guys, he's starting. Okay, that's it started.
All right. I hope everyone had another cup of coffee. I certainly had. I'm a bit hyper now. So in this session, what we're going to do for the next hour is we're going to look at heat transfer and OpenSees. Then we're going to jump right in and see how we can use a graphical user interface to build an OpenSees model. And then after that hour is over, my colleague Clark is going to show us how to do Timber in OpenSees, which is the topic of his research. Okay, so remember earlier, I said that there are places for you to find your documentation, and for OpenSees for Fire heat transfer, that we have a page that you can look at that contains some useful information on how we do it. And again, jump right into a problem. And this is a very, very, very simple contrived problem that you'll probably not do for research. But if you can do a simple problem like this, you can move on and do a little bit more complicated stuff. So what we have is we have a big block of steel. And what we're doing is we're subjecting it to some fire. That fire is heating this block of steel from below. And on the top, we have some ambient air going on, right? On the sides, nothing is happening. I know that's not how it usually works. You have things happening, but for this simple problem, nothing's happening on the sides, just bottom and top. And if we can do the bottom and we can do the top, you can do the sides and you can do more complicated things. And so we're going to work only with blocks, and that's because you can build almost anything from a block. We have more complicated shapes that you can see in our documentation, right? So what is the process like? And we're going to be working with a two-dimensional problem this time. And that's because in structural fire, in large buildings, most of the time you can get away with 2D heat transfer instead of full 3D. But yes, you can do 1 dimensions, you can do 3 dimensions. The commands will stay mostly the same, except you'll be, instead of doing lines, you'll be doing faces. And instead of doing a simple rectilinear 2D element, you'll be using a 3D element instead. And now, if you remember earlier, I said there is a small caveat that we don't always, although in OpenSees for thermomechanical analysis, we always build our nodes and then build our model. In that way, explicitly build the nodes, explicitly build the elements. For heat transfer, things are a little bit different. This was built, I think, in 2010 by our good colleague Yasheng Jiang. And so he said, let's instead of doing nodes and build the elements by ourselves, and you can still do that if you want to, let's create an entity, which is basically a geometric shape. In this case, it's a block, right? And then you tell OpenSees, I want you to mesh this block, and then you do your usual things, but you refer to the entities. And again, just like earlier, we will jump right into looking at an example. So what we'll be doing is we'll be looking at this small problem right here. Okay, I managed to do that. We'll go full screen. And let me just hide the things that are obstructing my screen. And so what I'll do is I'll close the things from the previous session, right? So we're no longer looking at thermomechanical. So I'm going to say goodbye, thermomechanical analysis. And I'm going to go. And this is what you'll see when you access. You'll have a session 1 file. You'll have a session 2 file in which you'll find the code that you want to use. So I'm going to go to session 2. I'm going to go to HT, which means basically heat transfer. For this section, I'm going to look at the template. And just like earlier, we're going to work through this with a template. So let's take a look at this template. What we have here, we have just some comments to tell us what we're going to work with. And we're going to say heat transfer into a block, and I forgot to continue that line. But then we're looking at a 2D problem. Gravity, we assume, is in the negative y direction, okay? And if you recall earlier, we had a command to wipe the memory. It was called wipe. For heat transfer, we have wipe heat transfer, right? So we can start with that. And again, we will start by defining some variables. You've already seen this. So what we'll do is we'll define some variables. We'll define a length of the block. And for heat transfer, you have no choice. You have to use meters, okay? Don't use millimeters. That's a common problem. And the reason for that is we have many of the constants stored in OpenSees that use SI units. So your temperatures are going to be Kelvin. Your units for length are meters. For mass, it's kilograms, and so on and so forth. I'm going to make this, again, a super thick block. I'm going to say it's going to be, was it 20? Okay, so it's not super duper thick. It's quite thick. So it's a really thick block. But what we have here, which is something we don't have before, which is we have number of elements in X, number of elements in Y. And that's because, again, in here, not unlike the thermomechanical analysis, we're going to be working with a mesher. We have an ability to mesh things. So for my X elements, I'm going to try and go for, or actually, let's make this 0.6. I'm going to make all my elements about 20 millimeters. So I'm going to have 30 elements in X, and in Y, I'm going to have 10 elements. So this gives us more or less square elements. And the better you shape your element is, the better. For here, we have also convective heat transfer coefficient, or heat transfer coefficient. For this particular problem, let us try going with something like 25. And we also have a heat transfer coefficient for ambient air. So if you recall, in our problem, we have ambient air on top. So we want to give it some coefficient. Unlike a fire, there is no flow and whatnot. So it's either 10 or 15, as you can find in the Eurocodes. Great. So just like in previous session where we created a dimension and we specified degrees of freedom, in heat transfer module, you don't need to create to tell it how many degrees of freedom. You just say it's 2D, 3D, or 1D, and then it will understand the degrees of freedom that it needs to create. The next thing we'll move on to doing is we're going to create that block. We're going to create that entity. And again, the entity requires some additional command, right? So if we go here and we look at this command above, it says create an entity, and let's create this entity. So we say create an HT entity, and we have type. And I forgot what the type is. So what I'm going to do is I'm going to click on this a few dozen times, and it will tell me, oh, these are my entity types. I have a block entity. Okay, so the command here is block. Right? And then tag. Again, tags in OpenSees is just a number. Just make sure you don't give two things that are of the same kind, the same tag. So if you create two elements, don't give both elements of their beam columns the same tag, because that's OpenSees is going to complain, is going to tell you, whoa, you can't have two things with the same tag. So just give it a unique tag. It can be 1, it can be 10,000, but at least it cannot be over whatever maximum number your machine stores for an integer. So basically 1 for now works. The next thing we find that you have to tell OpenSees where you want the center of your block to be. And this is super useful. Why? Because if you want to construct a more complicated shape, let's say you have 3 materials and they're all a bunch of blocks following each other. What you do then is you make sure that you place these blocks in the right location so that their faces match, so you can connect them together. For this simple problem, which has only one block, we're just going to say, well, it's going to be in the center of the block, which is going to be at, I place my corner of the block in 0, 0, and draw this block, and then I can calculate where that center will be. And let's see, how do you do that calculation? Do you have to do it in your head, or can you do it in Tickle? I think it's a much better idea to do it in Tickle because I can change the length and width of there for my object, and I don't want anything to change other than that. So for the center, I'm going to create these square brackets. And I'm going to tell Tickle, this is a Tickle command. I'm going to say, I want to create an expression. And for this expression, I want to use the value of the length because this is the center in the X direction. So I'm going to put this $sign to cache out my variable, to dereference my variable, get what's inside. So I'm going to type length. I'm going to say, I'm going to multiply this length by 0.5. Okay. And then the same thing for the center in the Y direction. So I'm going to say, again, another square bracket. I'm going to say expression. And this time is going to be thickness. We had specified thickness earlier. And again, I'm going to multiply by 0.5. Those of you who are familiar with some programming, the reason I multiply by 0.5 rather than divide by 2 is because Tickle sometimes complain about whether something is an integer or a floating point value. So I always try to keep everything a floating point value whenever I can. So I always try to have a dot somewhere. You don't need to do that, but I try to. And I think it's good practice. At least helps you to differentiate your tags from your non-tags. And then again, then what we have is, again, the length of the block and the width of that block. So if we were to look at the documentation, we find we have to specify a length and a depth, right? Or a thickness and a length. For me, it's going to be length and thickness. Okay, we cool so far? Great. Next thing, we want to define a material. And for OpenSees for Fire, you can define, I think, more than these, but this is a good selection of materials that I think you'll like. We have the carbon steel according to the Eurocode 3. We have concrete to the Eurocode 2. We have aluminum, again, I think Eurocode 6. And some fire protection material, spray applied fire protection material. We have like 5 kinds. Again, you'll find more information in the documentation. For this particular problem, we said it's a steel block, so I'm going to go with a steel material. Again, create an heat transfer material. This heat transfer material is of the type carbon steel Eurocode 3, and it has a tag which is 1. Now, someone asked me earlier, where are these material properties? So this is steel according to the Eurocode 3 properties. So if you just go to EN 1993 1, I don't know, 2 or something, you'll be able to find these material properties in details. And what happened is we just implemented these inside the code of OpenSees. Another place you can look for these things is the source code, and that is always open. You can always access that source code and see how things are implemented, particularly, I'm really bad at using the mic. And so particularly, you'll be able to see that carbon material is super easy to define. Okay, now we defined the material, we defined an entity. Now we want to tell OpenSees, hey, OpenSees, there is a mesh involved in this entire situation. So we define mesh controls. We tell it how we want to mesh this block. So to do that, we have a command to tell it how to control the mesh. And the mesh, even the mesh has a tag. But you see that it also has something called entity tag because you want to specify mesh controls for a particular entity. How do you tell OpenSees which entity it is? Well, by giving it the tag, which now can tell you if you have more than one entity with the same tag, why it doesn't work, because it wouldn't know which entity to assign the mesh to or anything. Another thing we need to specify is that the material. And again, here you can specify only one material, at least for this kind of entity. If you want to specify more than one material, you'll need to create other entities and mesh them and then make sure that they are connected together. So from the material, we have only one material we created that we care about, which is the steel. So that's one. Next thing you'll find we have an optional command for phase change, right? So for phase change, we can specify either, again, a true or a false. And what is phase change in this context? In this context, some steel, for example, undergoes some changes at some high temperatures. You get a spike in some of the thermal properties. So you either want to consider that or not. Same for concrete, you get evaporation of water. Now, the details of how these are exactly calculated, you will find in some of the papers that I can refer you to, but I can't tell you exactly how it's done from the top of my mind. All I can tell you is we calculate the entropy and we use that instead of just using the material properties as they are. We cannot do phase change from solid to liquid or from liquid to gas, though. So if you're going to ask that, the answer is no. Sorry. So I'm not going to consider phase change here. And then we have, I think, two types of mesh controls. Do we want to mesh on the number of elements or do we want to mesh on the size of the elements? Again, for me, because I want things to always be consistent, I'll use number. So I will remove, and when you see these brackets, these curly brackets around something, it means it's an optional flag, but you need one of these two. So number of elements, and I remember the variable we stored this was number of elements in X space and number of elements in Y. And if you stop here, you're in a bit of trouble. And when I prepared these and I was checking my files yesterday, it just wasn't working. And I was like, why is it not working? And I've been working with this program for like a few years now, right? I'm using it all the time. I build different components using it, and this file wasn't working. And that's because I forgot to mesh. Right? So you create a mesh, but you don't actually mesh till you tell OpenSees, okay, I created all my mesh controls. Now you can mesh. So you need this little command that says heat transfer mesh all. And that's, again, for the people that would like to use OpenSees and have not done so in the past, and you start to use it, you're going to run into problems. And then you're going to say, am I the problem or is it OpenSees the problem? And the problem is just sometimes it's difficult. Sometimes you will make some mistakes in this code, especially when you're new. So if you're new and you'd really like to learn it, and I have some of my students that have struggled sitting right here, don't worry, just keep trying. If you're really stuck, email me, I'll get back to you, help you out. Next thing, if you recall, we said earlier that we store our temperatures using Kelvin, and that's the case here, but our outputs will be in degrees Celsius, as we'll see later. So we have a command to set an initial temperature. That's the initial temperature that OpenSees will use as ambient condition. And then we have to specify heat transfer constants. And so if you do any normal small heat transfer problem, you need a heat transfer coefficient, you need an ambient temperature, you need some emissivity for the fire and some absorptive, I can't pronounce that, but you know what I'm talking about. For this problem, I specify two things. I specify constants for my fire, and I specify constants for my ambient conditions. And for both cases, I'm setting, the phi to 0.85 for both emissivity and absorptivity. And you can use whatever you like, I think, as long as it's below 1 or equal to 1. And the next thing is, in this problem, if you recall earlier, we said this little fire here follows the standard temperature time curve. My colleague will later show you how to use some other temperature models, some other fire models. Another colleague will show you how to use CFD temperatures or temperatures that he created in Excel. do your heat transfer analysis. But if you're wanting to use some of the very super common temperature time curves, like such as the standard fire or the hydrocarbon fire, then you can just say, I want my fire model to be a standard temperature time curve. And again, the number after it is just a tag, so you're able to refer to that fire model. After we create the fire model, we want to apply that to some place in the structure or in our problem. And how do we do that? Well, we say we use a heat transfer pattern. And again, this comes from just a finite element. You apply a load pattern. So a heat transfer pattern to you is just the way where we can apply loads. And we need those curly brackets to put the load in. So what we're going to do is we're going to do a heat flux boundary condition. I think these are actually, and maybe Limi can correct me if I'm wrong, but I think for applying load right now, the heat flux boundary condition is at least the most ubiquitous. It's the most common. But what does that mean when we use a heat flux boundary condition? Well, it means we're going to go to entity one, to entity of this number. And then we're going to do is we're going to look at the face of that entity. So the face, we look at different faces, phase 1, phase 2, phase 3, phase 4, and we're going to pick one of them to which we want to apply our boundary conditions. And all the other boundary conditions, for example, to set equal degrees of freedom between two different entities, will follow the same pattern. You have to give it a face. And then you give it a type. And here's when I wanted to talk to you about what is it? Is it like what do we give it? What does OpenSees give it? When you apply a heat transfer boundary condition that is convection and radiation, what this means is that OpenSees is going to actually expect temperatures, not heat fluxes, right? Why is that? It says it's a heat flux boundary condition. What it's going to do is do a simple conversion from your temperatures using your heat transfer coefficients. Assume if you specify radiation and convection, it's going to assume some that it will take that temperature. It will do the what was the equation called? The Q equals, and you will have the heat transfer converted into heat fluxes, but you don't need to worry about that. It will do it internally, and it will apply that as a heat flux. And then you need to tell it what are the properties you want for absorbability and emissivity. So, and what is the heat transfer coefficient? So you just say, okay, use these constants right there. There are many ways to apply these boundary conditions that Dr. Jiang has worked extensively on. My colleague in the next session and after lunch will walk you through some of these that are super useful. Some consider smoke, some are specialized, I think, for timber, and some pretty cool stuff. But for now, the simplest case, we'll do convection and radiation. And we'll also do the same for the ambient. And you will notice that we have two different types. We have a heat transfer pattern for fire, and we have a heat transfer pattern for ambient conditions, because we want our big chunk of steel to lose energy, to lose heat to the surrounding atmosphere on the side that is not exposed to fire. Next is, if you recall earlier, we had a recorder file, and that, or a recorder command that told OpenSees, which results do you want to store? And so that is done using, you need to give it what we call a node set. So because there is a measure here, you don't usually access the nodes by yourself. You tell it, I want the nodes that are located at this location for X, and at this location for Y, and this location for Z. If you don't specify a Y and a Z, it will go to that location that you specified in X, which will draw a straight line in that location. So here it is exactly halfway through the block, and it will try to pick all the nodes that are there, and it will keep recording the results throughout the analysis. You specify the file for which this node is going to go, and the solver is much simpler for heat transfer than it is for the structure, because you only need to tell it, hey, I want heat transfer with increments of some increments and some heat transfer solver, and I'm going to do it 120 times at intervals, I think, of 5 here, or 0.1. I messed up here, but don't worry about that. So if we go again and we 1 second. And we open our PowerShell from Windows and we go to OpenSees. Again, we have OpenSees, and what we'll do is I'll source our session2.tcl. And what it's going to do is going to solve it. And you can see that because I said heat transfer analyze 120 times at intervals of 5, it kind of overlooked whatever I said before. So it ignored my initial increments. And again, if I go here and look at session 2 output, it's okay. That's because there was an output before. Let me delete that. So if I delete my previous output, hold on with me for a second. My computer is lagging. So what I wanted to show you that if we were to just run this analysis and look at our output file is not going to be accessible. I tried to delete it now, so that kind of messed my computer up for a second, and that's because it's open. It's open in another file, so this is a locked file. If it wasn't created before, you will just have the file. It's going to be empty. Like we said earlier, we need to flush everything from the memory to the disk, right? So we want our output results to be printed. And I think my machine crashed. Okay, that is going to be an issue. Just give me a minute to just try and connect again. And hopefully this will solve the problem. Hopefully it's a local server issue rather than my computer crashing. And my computer has crashed. Nope, it didn't. Oh. Okay, so this is what happens when you try to be too smart and do everything remotely. So if I exit OpenSees as well, what it's going to do is going to flush everything to the memory anyway. I'll be able to delete this, but I'm just going to assume you believe me that it saved all your results. It did not, thanks to that small crash. But if we were to look at the results now, we will see that we get the results for all the nodes that we had created. And we'll see at the fire side, so at y equals 0, we have it's a bit hot at the top side. It's pretty much still at ambient, and that's because it's a really large chunk of steel that is being heated, and so it can take a lot of energy before it starts to seriously heat up. With this, we are done with the heat transfer section, and we are ready to move on to something I think is a bit more exciting, which is using a graphical user interface for OpenSees. Before I do that, however, I want to see if anyone has any quick questions. No? People online on the chat, do you have any questions? I don't know where the camera... Oh, Sensei, please. Yes. 1 second. I will come to you. And Sensei, I'll come to you.
I mean, yes, thank you. I miss you. Great miss you. So we even now it's all much. But sometime this
Right away. Right?
Okay, yeah. So what Sensei has just asked is when they do meshing, they need to have a more dense mesh near the fire because the thermal behavior is more interesting and it's more difficult to do the heat transfer analysis. Can you do that in OpenSees? The short answer is unfortunately right now, no. And that's because our mesher is super simple. It's super simple. You give it a number of elements to mesh in one direction and the number of elements in the other direction. I think Leeming,
Yeah, I can actually explain.
it seems Leeming has implemented a new measure without telling me.
Yes, we actually allow that because when we're dealing with heat transfer issues and boundary conditions, we need a fine mesh and that. So we provide a function in the code in the two codes that is a refine mesh. So there is a command called refine mesh, and we define it according to Cs. So it's a Cs for the mesh, and so we can refine the mesh for the like the boundaries. You can use that we can actually customize the seeds, the seed distribution, and then we can have a dense mesh near the surface. Yeah, so it is allowed to do that. But like normally we don't use it. We just use a fine mesh for the whole section because it's computationally efficient, and so we don't actually use a coarse mesh for the other part and a fine mesh for the surface. So just a fine mesh for all. So far that's what we usually do. So that's why Amber did not use this kind of function. Okay, right.
Still, guys, I am a steel guy.
For me, everything goes into the steel super fast. All right, so next thing is we're going to move into our graphical user interface. Go ahead.
There's a question.
Can flux time history be given as input? Yes, it can. And as I said, my colleague Nan Jojun, who's giving the lecture in the afternoon, will talk about that. But yes, we can do that, and we can do even a bit more than that. We can give, I think, heat transfer coefficient dependent on the temperature or on the velocity and flow conditions. But again, that is something that I will not cover. It's something that again developed by Leeming and is probably going to be tackled to some extent by my colleague in the afternoon session. Okay, so there is this program called GID, and GID what it is, and it's used for other programs around the world, like for SAFIR and for SAP 2000, for example. It's a general purpose graphical user interface. So it allows you to build graphical user interface for your solver as you like. Some great people in Greece built an earthquake version for GID. So we took that version, which is again open source, and we developed a Fire version for structures in Fire. So this is super easy to use. It's free up to 5,000 nodes. And I think after that, for an academic institution, it's like 60 euros a month or so. So it's quite inexpensive. To set it up, you can just download GID. You need to download the interface, the original interface for OpenSees, and then you download our interface. And it's a very simple process. You'll be able to do it, provide enough documentation for you after the session. Okay, wrong computer. There is an extensive set of documentation available for GID, the original GID, and the GID for Earthquake, which is pretty much covers all the primary commands you need to know to build a model. But for this session, what we'll do is we'll build a model that is for a structure in Fire. And we'll see how that's going to work. And what we're going to do is we're going to build a 2-bay steel frame. So it's just basically a bunch of columns, around 6 columns, connected with some beams. And there's 2 bays, right? And we'll see what that means. And what we'll do is we'll choose some elements, some members, choose some beams, and we're going to heat those with a linear temperature. We can do more interesting things, but for now, because we have just half an hour, we'll do that. And what you will find I provided is a long checklist. And the mic. So this slide contains a long checklist of things that you need to do step by step to be able to or to build a model with the least amount of errors that you were hoping to encounter. And what I did is I took that and I printed it out for myself so that as I go through this, it'll be more or less exactly what you'd be going through when you're building your own models. Of course, you can build different kinds. You can build shells, you can build floors, you can build tall buildings, you can import some geometry from other software. You can do some really fantastical things with this software, but we're not going to do fantastic things here. We're going to do simple things that show you how to do all the fantastic things when you build upon them. All right, is it full screen? No, it's not. Okay, let's full screen that. Okay, so once I open Git, this is what I get. This is the general interface, the generic interface that I have. The first thing that I'm going to do is move this away. It's hiding my view. The first thing that I'm going to do is I'm going to click save. And that's because I want to save the model somewhere. And you will see that many of your commands are locked behind the save, because you need to tell it where to store all the information that you're going to give it, right? So I'm going to call this session 2, and not going to say test, it's just session 2 now, okay? I'm going to save that. And what that does is just saves it. And then I'm going to go to this button here, this menu item called data, and it's called problem type. And what you see immediately, you have many different interfaces that you can download and use for this graphical user interface, but the one we're going to use is the OpenSees one that I have downloaded and already put on this machine, okay? So I'm going to click OpenSees, and that's going to start our Git OpenSees. And you what you immediately see is a bunch of additional commands or menu items that you will see. When you download it, you will not see all of these exactly the same. And that's because they adapt to the screen size. And also some of these are not yet fully available online for everyone to download because they're just under testing now. But all the things we're going to see here, you can do on your own today. So the first thing I'm going to do is I'm going to start building a model, right? And again, this is a very simple linear model, bunch of lines. So I will click the line command, and I'm going to say, I want my first node to be, or my first point to be at 0, 0, 0. Great. I want my next point to be at 0, 0. And let's give it a height of 3.5. And what we see is that it's still a point. What's going on? Well, I'm looking at it in the X and Y direction, right? So I will hold Shift and I'm going to move the screen by right clicking. I meant left clicking. And we see that we have built a line. Now, if you recall earlier, thermomechanical OpenSees, you build nodes and elements, not here. In Git, you work with it just like any graphical user interface. And so you're building a geometric object, you're building a beam, you're building a column, you're building a geometry that you can later mesh. And this is another reason why I don't really think OpenSees needs a mesher, because meshers are freely available. There are so many open source meshers that you can use. And just like here, our graphical user interface already has a mesher. Next thing I'm going to do is I'm going to create more columns. So I'm going to go to utilities. I'm going to Control C to copy. I'm going to say I want to copy lines, and I want these lines to be 5 meters apart. So this is the first point, the second point. So this is basically given the first point is at some coordinates. The second point would be at some other coordinates. What is the displacement you want? So by keeping the first one at 0 and just setting the second point y equals to 5, we'll just calculate the delta and we'll find that it move it by 5 meters, meters in this program. To the right. Do I want to extrude? Those of you familiar with CAD software know that if I extrude it, I'll get the surface. I don't want to do that. Also, you can tell it what kind, but I want to make more than one copy. I want to make 2 copies. And I want to maintain the layers. And we see that it copied it in the Y direction. Next thing I want to do is I want to copy it in the X direction. Again, 5 meters. I'll just be careful to just set it to 1. So we get 1 bay in the X direction and 2 bays in the Y direction. I think that's opposite of what I remember wanting to do, but that's perfectly fine for this. Okay, great. So next thing is I want to connect these with beams. So I'm going to again select the line, and I'm going to go on my computer. I'm going to press Control and A. And you see that the pointers change, and that's because now it will be able to hook onto these points to create our line. And I'm just going to create my floor beams. I'm not going to create a floor. I'm just going to create some floor beams, and it's quite hard to see here. So just 1 second. So my mouse double clicks, so it's saying you're selecting the same point twice. You're not going to get this error. It's my mouse's fault. All right, so now we have a geometry. If you look at your checklist, you'll find that I missed to define the units, but that's fine. I'm going to go to data, define units, and we already have compatible units set, but I really like SI with newtons and meters, and that's what I'm going to keep working with. And again, this is an issue with my resolution because I'm connecting remotely. I'm going to remember to save my work so many times because this is an experimental software, more or less, or a research-based software. So you will have times that it's going to crash on you. We define the units, we define the geometry, make sure that my model is defined in 3D. So I'm going to go to this place, set general data, modeling options. It says it's 3 dimensions and control in Z, and that's fine. So that's done. Next thing, we define materials, right? So how do we define materials here? We have different kinds of materials: steel, concrete, and multi-dimensional materials. If you recall, when we're doing a fiber-based section, we just need a 1-dimensional material because every fiber acts only in 1 direction. So we're going to define a steel material, go to this truck thing, and we make sure to create our steel. So I'm going to call it our steel, or actually, I'm going to say FY275. And you remember when I said earlier, you need to be very careful about your choice of units. In GID, you don't need to. So the GID has something to control the units. So when it says it's 200 gigapascals and this is 500 megapascals, you don't need to convert that. It will automatically do that for you. So I'm going to write 2. What is wrong with this? 275, and that's going to be fine. Then I'm going to remember to update changes. Okay, I'm going to create save. So now we have defined the material. We now move on to defining the sections. I know some of you are bored, but this is because this is exactly what we did for the script, but it is, I think, a lot faster and a lot easier, especially for more complex geometries. So we're going to go to this part, which actually shows a bunch of fibers. And what we're going to do is we're going to define our section. I'm going to call it a UB section, a universal beam section. I'm just going to call it UB. This changed, yes, please. And in here, if you see the separation equals 15 millimeters, don't worry about that. That is always there. Doesn't mean anything for you unless you're creating a back-to-back angle. And what we're going to do is we're going to keep all the same stuff here. We're not going to change the dimensions of the section, but we'll be able to see that for our section, for let's say this I section, and you can see that you can select the section from here. We're going to have 1 fiber in the flange and 6. Oh, this is the web. So it will have 1 fiber in the Y and 6 in the Z. And you can change those for the flanges as well. To save that and close.
Choose material, steel.
Ah, right. I forgot to update the steel material. So we created the material. So I click steel material and I make sure I select the one I care about. Thank you, Royu. And after I update it by pressing this button here, I don't need to worry about closing it. It's already updated. And I will save my, I will save my model. Next thing is we create an element, we define elements and we pass them this cross section. So we go here, this little beam, reinforced concrete beam thing is actually for defining elements. And I'm going to define a beam column element. In this case, it's a thermal displacement based beam column element. I'm going to call them my beams. Click OK. I'm going to save it. I'm going to go to section and choose the section that I have created, which was universal beam. I'm going to also save that. What I'll do is I'll use the same section for my beams and for my columns. Okay. That's just for the sake of time. I don't want to redo everything again to create a column. So what I'll do is I'll create line, assign now. So you created a section. We created the material. We created the section. And now we have basically created a beam column element. But still, what about the geometry? The geometry doesn't know I did any of that. Besides, which parts have these properties? You have to assign them. So you click on assign, and this kind of element can only be assigned to lines. Again, my mouse looks okay. Yes. And so they're red, click escape. And if you look here, it says assign 13 new entities to material my beam. So although it's an element type, in Git, everything is either a material or an action. Okay, looking at the checklist, we define materials, we defined elements, we assigned elements. Now let's not forget to assign boundary conditions. These handcuff things, and we go to points, and we're going to assign restraint. We're going to restrain the special points in everything. So we're going to select the bottom points. I'm going to fix it in everything. Rotation, translation, the whole thing. Okay, it says assign 6 new points. Come on. To close, I'm going to remember to save that. So now I have assigned boundary conditions. Okay, next thing we're going to do is we're going to assign analysis. So if you recall, we had defined our analysis object before. We said many things, what kind of algorithm we want to use, what kind of integration we want to use. Is it load controlled? Is it displacement controlled? Whatever. What we're going to do is we're going to make sure we have one solution interval for the mechanical loads and one solution interval for the thermal loads. You want to have multiple different kinds of loads, you can. You want to have an earthquake load, also you can. For now, we're just going to create those simple mechanical and fire loads. So I'm going to go to interval data. I'm going to accept the first one. It tells me what my system equation is. But for solution algorithm, again, I want a full Newton-Raphson solution. And I'm going to click accept. And then what I'll do is I'll create a new one. Yes. And in here, I'm going to call it thermal mechanical. And the only reason I'm giving it a name is because I wanted to put that name in the tickle file that it will automatically create for me. I don't want to use the band general. I want to use an oomph pack system of equations, and that is because it is a more robust solution method for this problem, or it's so it contains how the equations are solved. The names are a bit confusing, but this is another solver basically, although it's a system of equations. I'm going to accept. I'm going to close that. I'm going to make sure I am saved. So now we have two intervals, one for our mechanical load and one for our thermomechanical loads. And so now when we move on to assigning the loads, we need to be careful about which interval we're assigning our loads to. Because if you assign a load, a mechanical load, to the thermomechanical load, it means when your thermomechanical load is being incremented, your mechanical load is also being incremented. So you have to be careful, right? You might expect your structure to, let's say, move on until 500 seconds of analysis time or fire time, and then you find that you increased your mechanical load by 500 times. You don't want to do that. And again, the idea of assigning a file for temperatures based on time will be discussed in a later session. Okay, so what I'm going to do is I'm going to click on this time thing, and it says select the active interval. I'm going to go with interval 1. So for interval 1, I'm going to click this load thing. Resolution. And I want to apply some uniform load to my beam, to my geometry. And you always apply your loads to your geometry, never to your mesh. We haven't meshed yet, but if you have meshed, you might apply it to your mesh. And that means every time you mesh, all your loads are going to disappear. Make sure you apply your loads to geometry. Once you get some experience working with this, you're going to know exactly what I mean. So I'm going to apply a uniform force. And as we said, we are applying it in the Z direction. So I'm going to apply 30 kilonewtons per meter in the Z direction. I'm going to apply it to all my beams. Just by clicking them like that. And click finish, and you'll see it said assign 7 new lines with some condition. And if I forget later, I can just go here to draw. I'm going to say uniform forces, and it's going to tell me which elements have the uniform forces. If I click it again, and if I click draw again, I want to see the value. It says field value, local Z direction is going to tell me it's assigning it in -30. Or it says 30, but there is a small arrow that we can't see right now. All right, so we have assigned the mechanical loads. Let's assign some thermal loads. I know we have 9 minutes left, but we're almost done. We go again, we change this time to our interval in which we want to apply the fire. We go there, we do that, and I forgot to save in a while. I go again to the loads. I go to the lines, and I want to apply linear temperatures. Okay, and we said, I forgot what the loading we wanted to apply was, but let's just say we want the top of my beams to have a temperature of 100 and the bottom of my beams to have a temperature of 400. Before I apply that, I'll click change interval, and it says using interval 2. Okay, great. So that's what I want. I'm going to select, let's say I just want to select just these. Super weird fire that only heated these 3 beams, and that's because I want you to be able to see it when we visualize it. Okay. Now we save once more, and now we move on to meshing. Again, there are different ways you can mesh in GID. There are more sophisticated ways. You want to define your mesh, you want to apply more elements in the middle of the beam or on the edges of the beam. You can do that. You have an automatic mesher that can create non-uniform meshes. Basically, GID has its own mesher that will mesh its geometric objects. And then because you specify OpenSees elements to your geometry, when that geometry is meshed, all the elements are the corresponding OpenSees elements. So if you want to do more sophisticated meshing, you can do that from GID directly. The GID manual has very nice explanation of how their mesher works. They explain what algorithms they use. They explain what kind of options you can use. And again, there is a link to that manual here. But because it's outside of OpenSees, it can work for any kind of problem. So if you just want to create a mesh that has up to 5,000 nodes for free, then you can just use Git, and that you'll be golden. And it doesn't only work for OpenSees, works for anything. Okay, so let's create, we go to the mesh menu and we say we want a structured mesh. And we want to mesh our lines, and I want to assign a number of divisions. I'm going to just say I want 8. That means 8 elements for all of these geometric objects. Select them and hit escape. It goes back to that menu, and that's because it expects that you want to mesh things differently. So to help you out, it just goes back to the menu. I'm like, okay, now you can choose the next one. But if you look here, it says assign number of cells 8 to 8 to whatever number of lines we have assigned it to. Great, we have assigned again the mesh controls. Let us create the mesh. We go here, we click generate mesh, get meshing parameters from model. It will do some meshing and we're able to see a mesh. Unfortunately, there's no way to visualize individual nodes, but you do have your mesh. If you want to actually see the numbers that have been given, you can go to all on and say nodes, and now you see the number of the nodes. You can select which number of nodes you want to see, so you don't have to select it for everything. I'm going to say all off now. So right now we have created the mesh, we have assigned mesh controls, we have created a mesh. And we want to create a tickle file for analysis in OpenSees. So what we'll do is we'll go to Git plus OpenSees menu and we'll say create tickle only. Hopefully it will work. It says the tickle file was created. We close that. We go here, we press tickle, and it will go to the directory that we save, and it will open the tickle file. And this should look very familiar. It has all the commands that we had already created, but for hundreds of elements instead of like 5. Great, and then we are able to directly go and run our analysis. And that will start OpenSees, start our analysis. We want to post-process that. What we will do is we'll go to and we'll post-process. What it will do is it will read all the output files that are text, and it will convert them to something that can be read by the program. Proceed to post-process, and we're able to proceed to post-process. And what I will show you here is that indeed, when we go to a deformed mesh at the last time step, and I give it a big factor, let's say 10, and I apply that, we can see that our heated part actually deflected. Now, I know this was a super simple problem, but I think now, when you watch this recording later on, when you look at the documentation, I mean, we're super happy to help. Just reach out if you have problems. And I think you can build more sophisticated things that are for your own research. I think that's everything for me for now. I will pass you on for the next half hour to my colleague, Chung Chen, Cici, Clark, who will go through some timber with us. All right. Before I move to Clark, we have a couple of minutes. Any questions, online or offline?
May I ask if the thermal expansion is also included in your material property?
Explosion?
No, thermal expansion.
Yes, absolutely. Absolutely. There is no point in doing a thermomechanical analysis without thermal expansion. Yes. Okay, so let's move on to some timber. Oh, let's see. Any questions online? Cici, what do you want me to do? How do I help?
lectures, 5 hours.
Yes. Good morning, everyone. My name is Chen Chen. I am a second-year PhD student supervised by Dr. Li Mingjiang. And the topic of my presentation for today's OpenSees workshop is about modeling timber structure members in fire. As shown in the pictures on the structure, on the sustainable ability and aesthetics basis, timber can contribute to global carbon neutrality and green cities. However, the flammable characteristics will make timber elements to be the additional fire load and produce some fire safety problems. So therefore, there are some conflicts in using timber materials in constructions. Now, cross-laminate timber (CLT) is a type of engineering wood commonly used in constructions. It is usually an odd layer with symmetry. For advantage, it has uniform stress properties, good earthquake resistant performance due to the lightweight and better acoustic performance, thermal insulation and humidity regulations, and prefabricate components due to the high cost efficiency. Due to the naturally combustible properties, how could we assess the fire resistance of timber element? Previously, it mainly based on the test, but considering the high test cost, large investment of human and time consumptions, we can use numerical simulation to do this job. The open system for earthquake engineering simulation, OpenSees, was selected and developed by some research to OpenSees for fire in order to model the structure in fires. It has material libraries and different element types. It can deal with nonlinear processing, static and dynamic analysis. For advantage, it has faster calculations and high simulation accuracy, and it has easy convergence in the analysis of the complex structures. In order to model timber members in fires, we need to do two assignments. The first one is the heat transfer model for timber. We need to build heat transfer model for timber and to do the heat transfer analysis and to get the thermal response of timber sections exposed to fire, just like the temperature distribution, char depths, and layer distributions. And for the second step, we need to build constitutive model for timber to do the static load analysis at ambient temperature. With the help of the thermal load from the heat transfer analysis, we can do thermomechanic response, just like the stress strain curves and deformations. So the assignment for my job is to develop the heat transfer model for timber and develop the constitutive model for timber. This timber heat transfer materials and timber your code thermal model is my work. So I will briefly introduce from three parts as mentioned. The first one is development of a layer-based heat transfer model for timber in fires, including a case one about timber section exposed to fires. And the second is development of thermomechanic model for timber members in fire, including constitutive model for timber, mechanical property of timber at elevated temperature, and zone-based thermal action for timber beams, modeling procedure in OpenSees for fire for timber member in fire, and a case two about fire resistance of timber members exposed to fires. And the last one is a demonstration case about the composite timber concrete composite floor system in realistic fire scenarios. For the first part, the layer-based heat transfer model, there are many heat transfer model available today. The most important, the first one is the Eurocode 5, which is widely adopted, but its specific heat model only considers the heat consumption without the heat generation due to timber combustion. And it is only recommended for stand fire case only. And like the EC5 type models, it is modified from the Eurocode 5 model, and the disadvantage is it doesn't consider the heat generation either. And for the micro scale models, just like the GPero model, it is a very detailed model. It is not easy to integrate with finite element method too, because it has many complicated chemical reactions. So we need to develop a target model which is suitable for stand fire and non-stand fire scenarios. And we need to consider the heat effect due to timber combustion. And we need to record the real-time layer state. We name this developed model is layer-based heat transfer models. As for layer-based heat transfer models, it has three sub-models. The first one is layer model. It divided the timber section into 4 layers: white wood, dry wood, char layer, and ash layer with specific conditions. And the second one is the layer thermal property model for conductivity, density, and specific heat. It is a temperature dependent and a layer state dependent model. And the last one, and which is the most important contribution of this work, is the charring heat model. It will activate during the timber charring, and it will release heat, but the most heat will released to the environment, and a small amount of heat will absorbed by timber itself for inside heat transfer. This is case one about timber section exposed to fires. This is a simplified flow diagram in OpenSees to simulate the heat transfer inside timber sections. And we need element size, moisture content, and density to be the parameters for modeling thermal response of timber sections. And in the definition of the heat transfer boundary conditions, we have different fire model libraries, including idealized uniform fire, just like stand fire and parametric fire. And we also have the idealized non-uniform fires, just like the localized fire model and the natural fire model, which will be introduced in afternoon's reports. This is a script in simulating the heat transfer inside timber section. As mentioned by Dr. Anwar, we set different parameters to do this job. First, we need to define the heat transfer materials. This is the timber, and all the parameters And for the parameters,
all right, so that's on the presentation, right? Also open one. Typical file. Much better.
first thing we need to define the material is timber and with its parameters. And this is the moisture content. This is the heat combustion, and this is the time when the timber forms when the timber state from char layer to become ash layer. And for the second things, we need to define the dimension. It is the timber block width and timber block thickness. And for the second thing, is the heat transfer entity, which is introduced before by Anwar. And we do the mesh control, and we to activate the mesh and set ambient temperature and set the heat transfer boundary conditions and the heat flux boundary conditions. In this area, we can choose the different fire models, including standard fire, parametric fire, and localized fire, and some user-defined fires models in heat flux with first times, gas temperature burst times, and fixed heat flux. And this, we will define the heat flux boundary conditions in different phases. In this area, we can define the output, what we want to get. For example, we can record the timber char layer, and we can record the timber out time, and we can get the temperature inside different location of inside timber sections. As we all know, timber is a typical anisotropic material along different stress directions. It has 3 directions simplified to L, R, and T directions. And it was usually assumed as elastic plastic damage in compressive zone and brittle damage in tensile zone. And in our simulations, we selected the constitutive model developed by Gloss, and later the linearization of the compressive zone was done by Hennig. And we cite a rapid decline of the tensile stress on the right top with a small string range, considering the computational convergency. As for the mechanical property of timber at elevated temperature, we consider the reduction factors defined in Eurocode 5. As you can see, it is significantly different before charring temperature and after the before the drying temperature and after the charring temperature. And the maximum temperature call works with the heat transfer model to prevent backward state change of the timber layer when temperature declines. It means when the timber section experience temperature increase and after experience a cooling stage, its mechanical properties will remains to be the value when the temperature is the maximum temperature. And there are some limitations induced by the limited test data and the linear interpolation imposed. Transforming in OpenSees for fire, transforming temperature data from heat transfer module to thermomechanical elements need to use the thermal actions, and the beam thermal action 3Ds has been developed for timber beam and column with multiple sides of fire exposures. As you can see in this one, this is a picture for a temperature profile of timber beam with a 3-side fire exposure. After experience the heat transfer analysis on timber section, we can cite output files, and we can got the temperature data files, including 5 coordinate values along y-axis and z-axis respectively, and 25 temperature values at the grid composite of the coordinate position, just like this. This is y1, y2, y3, y4, y5 is the coordinate values, and the T1 to T25 is the temperature values, and the functions named gene interpolations developed by Dr. Anwar will be automatically performed to determine the fiber temperature with each cells of the grid. As shown in the formula, it is interpolated first along the y-axis and then along the first along y-axis to get this point temperature, and along this y-axis to get this temperature, and then interpolate along the z-axis to get the temperature at the fibers. As for the modeling procedure in OpenSees for fire, for timber members in fire, currently the TCO interpreter as a default choice is employed to interpret the input script to modeling procedure of OpenSees. As you can see in the blue part, this is the sightings we need to cite to for ambient loading analyze. We need to cite analyze type to 2 dimension or 3 dimensions, and define the nodes and define the timber material models, just like the uniaxial ultimate compressive, and the epsilon and epsilon 0, and the elastic modules, and the elastic for compression zone, and the elastic modules for tensile zone, and the ultimated tension stress. And we can define the sections and define the element and define boundary conditions. Then we can define the output and to do the ambient loading analysis. And for the right part, it is the heat transfer analysis. We can define heat transfer entity and the heat transfer material for timber, and define the simple mesh and define the boundary condition. In this step, we can choose different fire models, and we can do the heat transfer analysis. By combining the 2 parts, we can do the thermomechanical analysis and get the thermomechanical response of timber members exposed to fires. In order to check the developed heat thermomechanical models, we built the finite element models to do the uniaxial tension and compression test at ambient loading and fixed time loadings. As you can see in the picture of materials of degradation of timber fibers, you can see when the temperature increase, the ultimate stress will decrease with the temperature increase. This is the case 2 about fire resistance of timber members exposed to fires. And the test parameters is shown in the picture. And we have a cross section of 600 millimeters plus 150 millimeters. And the moisture is 12%. And the density is about 452 kilogram per cubic meters. And these 3 parameters is enough for our heat transfer analysis. And for the different, and for other parameters, it is 5 layers and the thickness was symmetric. And loading method is 2-point loading with uniform distributed load of 6 kilonewton per meter. And the fire condition is the stand fire furnace heating at the panel bottom. And the layer material is a sparse with SiF2022 stress grade. And in the Excel, we can see the recommendation values for the L direction layer of the SiF24 grade. And this is the ultimate compression stress. And this is elastic model for under tension and under compression and the ultimate tension stress. And the epsilon 0 is calculated by the, it means the string when the stress gets the ultimate compression. And for the T direction layers, it was suggested to taking as 10% of the L direction layers as in the report. Except for the elastic module, it was suggested by the test data. This is the script for thermomechanical model. We can set the different, we can choose different models. The first one is for thermomechanical analysis, and the second one is for ambient loading analysis. The difference has 0 because we can choose this one to do the ambient loading test, and we will define nodes, define boundary conditions, and define material with tag. In this way, in this area, we can define the different material of CLT. For the material tag 4, it means the L direction, and the other materials is the FCK epsilon 0 and elastic in tension and elastic in compression, and the ultimate tension stress. In this area, we can divide the section to 25 parts, and we can define the CLT different layers with fiber, with different fiber area. For this area is for L direction, and for this area is for T direction, because the thickness is 150, and we divide it to 25 parts, and different layers have different thickness. We can get the number area. Then we can define the coordinate transformation and define beam element and define output, just like the middle span node. And the fiber location defines the fiber location bottom and fiber location top. and we can get the deflection at the middle span node. Because we choose to do the ambient loading test, so we will ignore this one. This is for the thermomechanical load, and we can set the load at different nodes with corresponding values and to do analyze. And if we choose to do the ambient to do the thermomechanical analyze, we can choose the corresponding comment in this area and put our thermal load in this area to do the heat transfer model, to do the thermomechanical analysis. This is the range to get the thermal load, and this is the temperature as I mentioned in the thermal action. And for this demonstration case, it is about a composite member in realistic fire scenarios. It was inspired by the experiment by Harden, and the wood crab were replaced by the burners, and the definition of the mass loss rate follows the alpha test data, and we can see in the right picture the timber elements will take effect to the compartment fire dynamic, and the composite members were assumed as simple supported. And the main task of this demonstration case is to generate a non-standard fire development history. And when we get the time variant gas temperature and the adiabatic temperatures, we can do the heat transfer analysis for concrete slab exposed to one side fire exposure, and the timber beam exposed to the three-side fire exposure. And then we can do the thermomechanical analysis under uniform distribute load, and to get the thermomechanical response, just like the central deflection of the slab under different UDL, and timber stress at different locations of the middle span sections. Just like this picture is the thermomechanical response, and this picture is for the heat transfer analysis for concrete slab, and this is the heat transfer analysis for timber beam at different time nodes. These are my reference for this presentation, and thank you for listening. That's all my presentations.
We have time for one question. Questions to CC? You're super clear, CC. Okay, so we have lunch ready outside as usual, because many of us have the orange code, the amber code for leave home safe. We have special areas that are reserved for us. Thankfully, the weather is wonderful today, so we'll all sit outside together and eat. We have sanitized the area outside when we went into the workshop, so that you would find it's a little bit wet, but that's just because it's been wiped perfectly clean. There is vegetarian options, there is a seafood option, and there is a beef, I think. So if you like halal food, I recommend you take the vegetarian or the seafood option. I have explicitly asked to not have anything that's not a fish, or explicitly no alcohol with the seafood and the vegetarian options. if you really want a physical certificate, we'll send attendance certificates to everyone that came to this workshop. If you need a physical certificate, my colleague Sally has them. She'll write your name and you get a signed physical certificate. All right, thank you. Let's go eat and have some drinks. For those joining us online, I'm sorry I can't get you any lunch. Good get sir. Yes, of course. Everyone that's joined online has already been marked, and we will send you a PDF certificate. Any more questions? No, that's good. All right. See you all in next session. I don't remember when that is. 1:45. All right. Take care. I don't know. Guys, audio video thing. Yeah. That's with Atif. That's with check that we start on time this time. All right.
So that made chat first.
Discuss. I think this added to the group.
online 呢，是不是要连这个？
Okay,
但是这个怎么连？先连不了。
All right, guys, help Atif test. People outside.
Yes, sure.
那但是这个好像连不了。
Hello?
Hello.
Hello, where is my video? Where oh, now I can see. Okay. Can you hear me?
Yeah, we can hear you.
Yeah.
Okay. Okay, can you see me as well?
Just testing.
You can share the screen.
Okay. Okay, just I can share screen, yeah. Let me please make me I'm disabled. Not disabled. My first screen is disabled, okay.
Just went there like 2 days. What happened? Was it the surfing?
This was not surfing, man, it's boating, yeah. Come on. I'm not able to do surfing ever.
Nice. Can you see me, Atif?
Wait a second. There's
Oh yeah, that's the camera right there.
no, I can't see. I can see you're walking on behind and you have something in your, yeah, I can see you. Can anybody make me host or co-host so that I can check my sharing?
And plus, I will prioritize because whenever I have to do the autoclave for the climatic jumper process, so I can just, like I have to prepare. Yes.
这要不要靠到老师？
电视吗？它自动连到那个上。
会说吗？
Yeah, that's true.
对，就是插上这个电视之后，它就自动放到这个上，应该是一个电视。
就是你把这个麦放到这个，
这个遥控可以开吗？对呀，可以开声音吗？
可以。但是声音我觉得应该还是要这个教室的。等会儿之前没用，是不是用错？哦，没有用过。这个就放这儿吗？没有。Hello.
Hello, can you please help me to see? I can share my screen.
Yes, please.
About
应该需要给他一个 call host。
这个不用给他这个还是能。
yeah. No, I'm not gonna be
需要给他 call host。
点这个 off 它应该是可以的。是讲这个。
Yeah.